All right, so what we want to do today is talking about another kind of motion, which is the simple harmonic motion. All right, and what we are going to do is we are going to take a look at what kind of simple harmonic is and how can we set that up. All right, and once we're done with that, that will lead to the explanation of waves. All right, and once we're done with the mathematical description of waves, then we can study some properties of waves, maybe some superposition, what happened when they meet, how they add it, how they subtract it, on and on. Okay, and that will be the topic of waves on strings. And later on, we'll talk about other waves as well, about sounds, about optics, which is about light wave from the perspective of waves properties. Okay, all right, so today it's going to be a lot of mathematics, and I don't know you like it or not, but I think this is something that we want to start with. Guys, I have a very simple system over here for you. Spring, I don't like that. All right, not too bad, not too bad. But once again, I just want to show to you that once you understand this simple harmonic, all right, because you guys, and many of you are from computer science, computer engineering. I mean, this is a very good mathematical system to study because it's going to be fundamental to stuff that you have to do with anything that is oscillating at all. Which, I mean, the easiest example for you guys is sound. So later on, when you want to do the signal processing, and when the signal is in the waves type, like sounds, like, something has like periodic properties, you can use this kind of mathematics to be your fundamental stuff, and then you build on top of it, on and on. All right, it's going to be fun, guys. I guarantee. All right, so the system is simple. You have a mass attached to the spring, and everyone knows that we use Hooke's law, right? You guys still remember? Spring force depends on some constants. We call it the spring constant, K. And then you just multiply by the displacement of the spring. It depends on spring is being stretched or is being compressed. But doesn't matter if you put them in terms of the vector. I can put an arrow on top. So what you have over here is actually the spring force supposed to go opposite all the time. So once you turn this into an vector equation, then you need to put a negative sign in the front. Cool? All right, so that means if you look at this one, the displacement is positive. So it says, no doubt, the force is pointing to the left. This is a negative direction. On the other hand, if you don't have any stretch or compress whatsoever, so the spring is at equilibrium, there's no force, no problem, zero spring force. On the other hand, when the spring is in a negative displacement, then the force is pushing in the opposite direction, so it's going to be positive force. All right, that's easy enough. All right, so this is a very, very simple system. What you need to do next is just equate this to MA. Isn't that cool? I don't have sound effects set up anymore. I used to have like a sound effect here. All right, but anyway, so what you have over here is, all right, Adan, sigma F equal to MA, but you only have a single force here, which is a spring force. So you just set that negative Kx equal to MA, and then you're done. Not only that, on top of it, Adan, you're only doing it everything in one-dimensional movement. So you don't even have to care about the y direction, the z direction. So everything is under x direction. So here we go, guys. I can just write it out as a negative kx. This is a vector equation, but along the x-axis, equal to mass times acceleration along the x-axis. And that's it, guys. We're done. We call this equation of motion. And this is the connection to Newton's law. Cool? Easy enough? All right. Question. Can you solve this for me? I want you to solve this equation for me because it's an equation. So whenever you have an equation, you're supposed to have a solution for it. Give me the solutions of this equation. Ta-da! All right, that's it. That's the key things that we're going to learn today. All right, so today is going to be a weird type of lecture. All right, I'm going to just probably talk a lot about mathematics and all this stuff. So I'm going to show you how to solve this one, even though down here, I already concluded that what type of solution is going to be. But I think it's very interesting to take a look at this. So let me add a page here. Okay. And I'm going to ask you a very simple question right here. So let me do 2 pages. All right, guys. So look at the equation one more time. What did you see? You see negative kx equal to m times a. All right. I don't have to put the subscript x anymore if I don't want to, but everyone knows it's along the x-axis. And everyone knows the answer relation is a second derivative of this position over time. So it's going to be d2x by dt2. Everyone's good? So that means the equation that you are looking at is going to go like this. I rearrange this one to make it look like this. Plus, or actually, if you don't like plus, I can put an equate to negative k over mx. All right, guys. Now this is your job. So this is the equation that we want to attack today. What is x, right? That's what we want. When you want to solve for things, this is what you want to solve for. You want to solve for x. But the only problem of this one is it's a differential equation because you have the second derivative term right here. All right, so it's a second derivative. So the only question you need is like, what kind of function of x that once you get differentiated twice, you have to differentiate it twice. You get the original back with the negative sign with a factor in the front. You see what I'm saying over here? All right, just to make things a little bit simpler, think of it this way, guys. Here we go. All right, I don't know my approach is going to work for you guys or not, but I hope it works. If I have only this simple equation, so this means I just set the numbers in front of x to be just number 1. There's no k over m anything, it's just 1. What kind of solution of this? I mean, what kind of function that will be a solution for this equation? What do you think? So you have to imagine like what are the x's that get differentiated twice and get the original x back with a negative sign. Now, think about it. Functions that you have learned in the past, it's either polynomial, which doesn't work. I mean, when I say polynomial, or I can say a power function. So you can start from like x to the negative 2, x to negative 1, numbers, x squared, x cubed, on and on. Doesn't work because every time that you differentiate this, it's gone. It won't get you back the original x. Another kind of function is, well, Ajahn, think about it, not a lot, but well, I can do like exponential, e to the x, yeah, exponential. Well, e to the x or a to the x type almost work, but everyone knows if you differentiate e to the x, you get back the original without the negative sign. You guys with me now? Yeah. All right. Some of you already got the answer there. Yeah. The only class of function you might say about that. What about logarithm? No, that's still bad because whatever log of x or whatever at the base of log doesn't give you back any original function. So the only thing left for you is this. It's a trigonometric function, guys. All right, this is like a big wow right now. No. All right, so from the look of it, probably is either sine or cosine of that, because the derivative of sine, you get cosine, and derivative of cosine, you get sine back with the negative sign. That's it. That's what you want. So at the end, there you go. The only class of function that is going to work is sine or cosine. Isn't that cool? When I say isn't that cool, it means, think of it this way, guys. You start from sigma f equal to ma. You get the equation of motion. Once you solve the equation of motion, you get the del behavior of this, sine and cosine. It's go back and forth. Mathematics is already there for you. Equation is already there from Newton's law. So that's it. That's how you describe the nature. All right, guys, this is a wow moment here, I think. All right, but anyway, our job is not done yet. But then this is easy because your coefficient in front of x is just number 1. All right. So what if you have k over m in the front? What will you do? All right, here we go, guys. So it's going to be a lot of fun now in the sense that go back to your calculus course. Remember this, sine ax by dx. What do you get? You get cosine ax. But then you have to do the chain rule, right? Remember the chain rule? Dip side. Yeah. You have to differentiate the whatever the function is still not x. So that's why you get extra a in the front. With me? So far so good. But then it's not done yet because you have to do 2 times. You differentiate that one more time by dx. One more time. So this is your second derivative of the original sine ax. You get a, and it's a constant derivative of cosine, you get negative sine. And then you have to do the chain rule one more time. And that chain rule gives you extra a. So you get negative a squared sine ax. Do you see what I see over here? That's the sine ax. And that is the original function that you start with. See that? So that means every time that you squeeze in the factor in front of x, after second derivative, that factor in front of x will pop up in the front with the square in it. Isn't that cool? So that means when you go back to your original equation that you want, the factor that goes in the front is k over m. And that leads you to conclude that, so I know x must be, everyone still follow, right? Sine square root k over m x. Isn't that cool? All right, by having that square root k over m in front of x, is guaranteed that once you do the second derivative, the k over m will pop up in the front. Okay, not yet. But think about it. There are a couple of things that we can add on top of this. First, all right, I'm just too lazy to write this one as a square root k over m. Let's talk about this as some number. So what you can do is just saying that, let's call this omega. That's something that you can do all the time. All right. And the second thing is, I think I found one mistake of my time. Sorry, guys. Okay, it's not a mistake, but I think this is what you're familiar with, I think. Back in the day, when you study calculus, most of the time you're doing the derivative with respect to x. So this is usually you call it y as a function of x. But if you notice, what we are doing right now is an x under the variable t, all right? So at the end, we're going to have to rearrange everything back to be x against t, okay? Even though right now, what I'm saying to you is the derivative with respect to x, which is what you guys are familiar with, right? Okay, you guys with me, right? Okay. I didn't sort of put a note here earlier. Sorry about that. All right, but anyway, I think you guys get my point over here, that all you need for that extra factor is just taking the square root of that and, you know, plug it in here. That will be good. But I have an extra thing that I can add all the time. I can multiply this with a constant all along. Doesn't really matter. I can squeeze in any constant to it. It doesn't change a thing. With me, guys? So that means my answer or my solution to my equation can be, you know, multiplied by a constant in the front. It doesn't really matter. And that's one thing. The second thing is, Ajahn, it doesn't really matter because everyone knows dx equal to dx plus whatever. You guys with me? When you have derivative of x, or you want to have the derivative of x plus a constant, they are the same because the constant doesn't really give you any change. So that means the x that you are seeing over here can be turned into something else like x plus degree plus something. It doesn't really going to change anything. All right. So I think we got all of the components to be in here. So let me wrap up one more time in case I speak about a couple of things all at the same time. So conclusion goes like this, guys. So let me do it one more time. I think I'm gonna just add a page. I want this to be big because I want you guys to see this one very clearly. All right, one more time, guys. The equation that we want to solve that derived from Newton's law looks like this. It's d2x by dt2 equal to negative k over mx. With me? All right, so now we coming back to our original equation now. Okay, there's a question comes in. It's a sine omega x, not a sine omega times x. Yeah, omega and x supposed to be together. Yeah, you're right. The first one is good. All right, so I will rewrite it here again. I hope it's clearer. All right, here we go, guys. So what is going to be our x? So I say first, x equal to, I pick the sign at this moment, sine, whatever goes in the front can be squeezed in here. So this is going to be omega squared. You guys with me? Because I am going to squeeze omega down here. And so that means my omega is square root of that factor in the front, root k over m. Cool. But because now your free variable is t, so I'm supposed to put t right here. Then there you go. And as your friends just mentioned, it's supposed to be omega times t. And then I say I can add any extra constant in the front, doesn't really matter. Okay, plus I can actually add anything toward the back, doesn't really matter. It doesn't change anything. And that's it, guys. This is the solution. I put like 3 stars in here. Bam, done. All right, isn't that cool? So just from Newton's law, this is what you get. This x describing the movement of the mass attached with a spring. And you can see it's oscillating. It's sinusoidal function. So if you want to plot a curve, it will go bam, bam, bam like this. And that's perfect. However, you might be asking, wait a second. Why did you pick sine in the first place when you also have the cosine that behave exactly the same? Because derivative of cosine is negative sine, derivative of negative sine, you get the negative cosine. So that means d2 cosine x by dt2 is also negative cosine x. So but then cosine behave the same thing as sine. The answer is, yeah, up to you. It doesn't really matter. Go for it. You can write like this as well. No change. The only thing that is going to look different is if you write it as a cosine, you just start from different position. That's all. You guys with me here? Not only that, because you already have the delta. So that means you can pick to start at any point. So my conclusion is my sine or cosine are actually equivalent. So I hope this will clear things up. In the future, when you look at the textbook, some textbook will refer to the solution as a sine, some textbook refer to the solution as a cosine. Doesn't matter, they are exactly the same. Because you can adjust your curve anywhere you like by adjusting the delta. There is some delta that you can play with all the time. You guys with me? For example, okay, let me clear things up one more time. If I have sine, just let's say I'm just saying that sine t plus pi over 2. Remember this relationship over here? You guys remember that this give you cosine. See that? All right, so this is the identity from trigonometry saying that, hey, when you have sine t plus 90 degree, you just switch from sine to cosine because you slide the cosine, slide or shift the sine function by 90 degree. And it turns out you're going to get a cosine function. And of course, if you have a cosine function, and then you want to slide it 90 degree, you're going to get a negative sine t. So my point is, well, they are exactly the same thing. by sliding the stuff around. See that? I hope you get my point over here. Sine or cosine doesn't matter. Once you have that extra delta, you can play with it. Just sliding back and forth, left and right. You can pop up the Google and then just write down, or maybe if you have like a simulator, some sort of like a math simulation that you can do, play around with the parameters of the sinusoidal function, cosine function. Yeah, that's it. Okay, so I hope this cleared things up. That now in any textbook, they could write down the solution to be in the sine form or cosine form, doesn't matter. As long as you have that extra delta in the front, you are good to go. Cool. All right, guys. So that's it. That's my long explanation to this. Here we go. All right. So I hope this get back to our business, saying that, hey, if you have whatever factor that goes in the front, square root of that can be called omega. And we just said sine or cosine means the same thing. You can pick any one of those. All right. Once you pick those, then there you go. Your final solution will go something like this. X equal to A cosine or sine omega t plus 5. You're done. All right. But before we're going to call, I mean, you guys kind of know from the slide that I'm going to call this simple harmonic motion now. But before we get to that, hey guys, what is the unit of omega? Let's just go back to the feeling of the last trimester. Just talk to the webcam right now. Hello. All right. Okay, what is the unit of omega? How about Ajahn, every time that you have an argument, oh, thank you for the word answer, very nice. Yeah, because every time that you have anything that follows sine, cosine, exponential, logarithm, those quantities must have no units. All right, you guys with me? Right? Because for example, you never have seen log of mg before. No, impossible. You're never going to have like an exponential of like normal force. No, that's not possible. Anything that follow log, exponential, trigonometric function must have no units, right? Because we never gonna have like a like log of Newton or like exponential joule. Like we never have it. Not possible. So that's why whatever that goes in here must have no units. But we have already know that t is second. So the omega must be 1/2. So that means it's going to interpret it as frequency. However, we learned about this. It depends on the units that you pick. If you pick the SI system, the angle that we're talking about is in radian. So that means this is going to be the same thing as the radian per second. And that is your angular frequency. That's it, guys. So the interpretation of the omega is an angular frequency. And of course, you can always use 2 pi f or 2 pi over period, just like what you had before back in the day of circular motion or anything that run periodically. Yeah, just say, okay, all right, go back and forth, back and forth. So if you know frequency f, multiply by 2 pi, you get radian per second, and that is your omega. See? So actually, omega has the meaning in it. And what does it really mean now? You go back here, Ajahn, we just call omega to be root k over m. Do you see the amazing what of like properties of simple harmonic motion yet? So what I'm seeing over here is this, guys. If you have one spring with a specific value of k attached with a mass with a specific value of mass m, you cannot change the way that it oscillates. And wow. So when you have a mass attached to a spring with a constant spring k with a mass m, you set it in motion. Now it's guaranteed it's going to bounce back and forth, oscillating back and forth according to sine or cosine behavior. So it's gonna go bow, 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 bow. But you cannot change the frequency. No matter what you play around with it. You can stretch it more, you can stretch less. Once you let it go, it's gonna bounce back and forth with the angular frequency of root K over M. Cannot be changed, guys. Amazing. And that's why sometimes this is being referred to, this is the natural frequency. Whoa. All right, and we're going to have a chance to talk a lot more about natural frequency later, but that's what it is. It means is naturally oscillating at this frequency. You cannot change it. It's a nature of this system. The only way that you can change the omega is changing the K. So then you have to bring in a new spring or put in a new mass, changing the mass or whatever. You have to change the K and the M to get to a new value of omega. Isn't that cool? All right, so I hope this, I don't know, I think it's kind of like showcase the power of Newton's law. It's like only sigma F equal to MA give you everything. Amazing. Wow, wow, wow here. All right, too many wow today, guys. All right, so I hope this wrap up the form of the final solution, guys. This is it. This is the solution of our equation of motion. A cosine omega t plus phi. And that is simple harmonic motion. You might be wondering, why is the name? Why do you call this simple harmonic? All right, first thing first, the harmonic is, think of it like a frequency. When you're doing like a musical instruments and other stuff, they have many harmonic, and usually harmonics mean frequency. But when you say it's simple harmonic, mean it's a very simple frequency system. So it's a motion with single frequency. And that frequency is omega. Done. Simple enough. Cool. All right. So, but you might be wondering about that. Is there any not so simple harmonic? Yeah, of course. There will be instrument sound from musical instrument doesn't gonna go with the sinusoidal wave. It might look like this, even though it's a periodic, but the shape of the wave is not gonna look simple. All right. And for those of you that going to do signal processing, the way that I speak, hello, if you bring on an app that detects the sound wave, the wave will look ugly, but it's a wave anyway, so it's still periodic. But the shape of the wave is not going to be a simple sinusoidal function. So that's why the real wave is not going to be simple as this one. So that's why every wave that can be described using sine or cosine function like this, we call it a simple harmonic motion. Simple enough. Yeah, monotone, very good. Super monotone. So the only way that you're going to get something monotone like this, your instrument must be simple as well. Because the sound coming out from, for example, our vocal cord or from the guitar, piano, and all this stuff, it's not so simple. So that's why they composes of many harmonics. So that's why, you know, there are higher harmonic sound, lower harmonic sound that built into the net wave that's traveling out. So it's not going to be super simple. All right, very cool. All right, thanks for the comment. Very cool. All right, monotone is nice. All right, guys. So once we know with this, so what's next? The next thing is going to be quite simple now because you know everything. When I say everything means you know the function of the position. So you know exactly where the mass is supposed to be at any time. So if you know exactly the position of an object, you will be able to calculate velocity and acceleration very straightforwardly. Yeah, you guys remember this is like bring back maybe first lecture in physics 101 maybe. Right, but anyway, for us, I remember if you know x as a function of time, you take derivative of x with respect to time, you will bring up the velocity of that mass. So all you need to do just differentiate x with respect to time once. Everyone knows how to differentiate, yeah? Derivative of cosine, you get negative sine. Don't forget the chain rule, give you extra omega in the front. A stays there. That's it, guys. That is your velocity. Simple. Nice. However, there is one thing that we can extract from this right away. Look at the numbers in the front. Because everyone knows sine and cosine function never go beyond 1, never go below 1. So that means the velocity will never go beyond this value right here. It's going to bounce fast and slow, go to 0, flip the direction, doesn't really matter. But the maximum that you're going to get is going to be that omega A. Cool. Do it one more time, guys. If you differentiate this one more time, you're going to get acceleration. So dv by dt. Derivative of sine, you get cosine. The negative sign stays there. Chain rule give you extra omega. So the omega square is in the front. A is right there. If you do the interpretation just like what we just did, yeah, then that A omega square must give you the maximum acceleration possible. See, I don't think anything else can be more simpler than this. More simpler. What is that? Simpler than this. It's more simpler. What the heck? All right, guys. Cool. So that's what you get right from. So far, so good. I haven't done anything more than just Newton's law, believe it or not. All right. So the figure on the right is showing you the sequence of the movement of this mass on the spring. All right, but you have to make sure that you understand this correctly. Let me ask you guys, when the velocity of this mass is 0? Well, of course, Ajahn, it's going to be 0 at the two ends. Whenever the displacement is at the maximum, because that is the position where the mass is about to turn from one direction to the other, and that is the position where the velocity is 0. So velocity is supposed to be 0 at these two ends. You guys with me? Cool. And the maximum displacement that you can go, which is the A that we have been using all along, you can call this amplitude. You probably have heard of this before. It's the amplitude of the oscillation. All right, so that's your A. So that means the maximum velocity of this will happen when? It's going to happen right at the center or at the equilibrium where the mass is going to travel at the largest speed of omega A. Cool? So you can imagine that it's going to go vroom, and it goes stop to 0, and vroom, it's going to stop at 0, and it's a vroom, stop at 0. All right, this is a really bad physics demonstration ever. But anyway, I can switch the screen and then bring up, like, you know, some nice simple harmonic motion simulation. But I think this is the as organic as you're going to get. It's then vroom, 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 vroom. So at two ends, my hands had to stop. And in the middle, that's when that's the quickest, fastest velocity. That's it. All right. On the other hand, what about acceleration, guys? Where are you going to get the highest acceleration? Of course, the situation is going to be opposite. The acceleration is going to be max right here. Why? Because that is the position where you're going to want to flip the velocity. So that's when the acceleration is going to be the highest. All right. But you can think the other way around, but then it has to happen at the amplitude, because if you go back to Newton's law, sigma F equal to ma, the force is going to be biggest when the spring force is the biggest. And how can you get the spring force to be the biggest? You have to bring up the biggest position of the spring, which is the amplitude. You guys with me? All right, so that's why at the amplitude, the force is the largest. When the force is largest, the acceleration will be the largest as well. So that's what it is. All right, so at the amplitude, that's where the acceleration is at the maximum. And where is going to be 0? It's in the middle, guys. A vroom thing, even though it moves fast, the velocity is at the maximum, but they don't have any acceleration at the center. Why? Because at the center, spring is not stretched or compressed. So there's no force. No force, no acceleration. So at the equilibrium point of the spring, the speed is at the maximum, the acceleration is at the lowest, which is 0. And that's it, guys. Wrap up simple harmonic motion for us. Is that cool? I think this is very cool because everything just came from Newton's law. I think so. I think this deserves like an applaud or something, or wow, 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 or some emoji or something like that. Yeah, I think so. Thank you for participation there. Oh, there's a crying. Not crying emoji. I thought it's like light bulb emoji or something. All right, guys. So, but anyway, that's good stuff. Now, all right. So I think we're going to take a quick break, maybe just only 5 minutes because I was so late. This is my bad. Sorry. All right, but I'm just gonna run, grab some drink, and we'll be right back. But in the meantime, while you're waiting, sitting comfortably at home with your drinks, coffee, and snacks, answer me this question, guys. I want the same thing, but with pendulum. All right. Oh, emoji keep coming. Very good. Thank you very much. All right. All right. So we want equation of motion, but now it's a different system. It's the pendulum. Whoa, whoa, whoa. All right. And everyone know pendulum swings. So that means you get oscillatory behavior. Everything go back and forth, back and forth. It's periodic. So you can imagine in your head, this is going to give you simple harmonic motion as well. But what will be the shape of the function that is a solution of this system? Isn't that sort of like exciting? Yeah, waiting to see. Yeah. All right, guys. So I'm going to get something to drink here. Find me the equation of motion of this pendulum swing, and I will give you the answer after the break. All right. So let me pause the recording for a little bit. See you in 5. Okay. All right, guys. So I'm going to show you how, once again, to apply the Newton's law. And actually, I already got you like a big hint up here. So if you look at this one, and if you look at the movement of this, actually, there are a couple approaches that you can do. All right. But if you want to stick with the analysis of the Newton's law in like a translational way, so that means you can imagine that this mass is kind of like traveling like on a like an inclined plane at this particular moment, something like that. And then you're trying to draw all the force that acting on this mass, right? So you have mg pointing down, you have tension pulling up, and because all the movement is along this tangential direction, so let me give you like some sort of like the direction of motion. It's sort of like going downward like this, right? So you can imagine that you can do the free body diagram and then do the analysis just like the mass on an inclined plane. So that means what I can do is I can break the mg into 2 components. That's an mg sine theta over here. And then I have the vertical component right there. I can just discard that component there. See? All right, which is pretty good, pretty good. That's not too bad. Okay, and because of course the vertical direction, vertical means perpendicular to the direction of motion, must be nothing. So in that case, you can say, okay, tension must be equal to mg cosine theta. All right, but that's done. And then when you look at the direction of motion, sigma f is just mg sine theta. However, there is the direction associated with it. If you prefer to say it's pointing to your right, shoulder is positive. So the mg sine theta must be pointing in the negative direction. So that's why you put the negative mg sine theta right there. Cool? But that's the only force acting on this mass. So that's it, Atan. Sigma f equal to ma, and I'm done. So sigma f is negative mg sine theta, done, equal to m times acceleration. But because this movement is along the circumference of a circle, so it's just a tangential displacement. Instead of calling it x, let's call it s. It's just like a path along the curve. That's fine. So your acceleration is going to be your tangential acceleration. d2s by dt2. Well, John, from the look of this one, I think I'm getting pretty close. Mass cancel. And let me rearrange into the form of the equation that looks just like mass on spring. Well, John, I can get it to look like this. And this is when the reality hits hard, guys. You cannot solve this one. This one is not solvable. No. All right, you need computer, and we need, like many of you guys, computer people to do this. However, when the angle is small, I don't know, for those of you that learned a little bit of physics back in high school and then did a little bit of simple harmonic motion, you might have heard of this sentence saying that, well, hey, let's say that the angle of the swing is less than 10 degrees, or I mean, the angle of swing is small. So what happened when things are small? So look at the sine theta. All right. So when you look at the sine theta, so let me write on the side over here. When you have a theta, sine theta is the height over the hypotenuse over here. Let me call it the z right now. So the sine theta is going to be h over z. But then when the theta is small, imagine this. The theta is small, like that. Now you start to see that your h is going to be this big, your z is going to be the hypotenuse right there. But now the base down here and the z are about the same size. All right. So that's one thing. Oh, then, that's not bad. That's not bad. So when the theta is kind of small, you can pick to use the hypotenuse, or you can use the adjacent. It doesn't really do any difference much. And now you compare this to another figure that you might have remembered, but by definition, the theta is just the arc length divided by the radius. All right, so let me put sort of like overlay on top of this is r. All right, too many parameters on here, but I hope you still follow. All right, so originally the theta is just the arc length. Let me call it the a divided by r. So the theta is arc length over r. But now, once everything gets very small, you come down here, guys. See the red one. Well, Ajahn, it looks like when the theta is small, it doesn't really matter. You're going to call it the edge, you want to call it the arc length, you're going to call it the base, you're going to call it the hypotenuse, or you call it the radius. They're sharing the pretty much like, they're not sharing the same thing, but I mean, the height and the arc length is going to get very close. The base, the hypotenuse, I mean, the base means the adjacent, the hypotenuse, and the radius are about the same. So that's why I can conclude that when theta is small, this dude right here is approximately equal to the theta itself. Does that make sense? All right. So when I do this hand thing, it's like, I just remind me of myself, remind me of that dude on the TikTok, right? When he tried to do things simple, I don't know. I think he's kind of like have like an NFT of himself or something already. All right, but anyway, the point is, so I can approximate the sine theta to be about equal to the theta. When you don't have any sine theta in there, that's a lot easier to solve, because differential equation with sine, cosine, logarithm, exponential is hard to do. All right, so that's done on the left-hand side, but now on the right-hand side, Bajjan, you still have S. So that's no big deal, because you come back here, see that triangle over here, bam, bam, bam. Oh, what is going on with my pen here? There you go. Look at that, my triangle right there one more time. By definition, angle is going to be equal to the arc length over radius, right? We could just reuse that definition here. So that means I can express S as theta L. Cool. Plug that in, guys, and see what happens. So you have d2 of theta L by dt2 equal to, with approximation, approximately equal to the negative g theta. Now here we have theta on both sides. I can move L to the right hand side, and I'm pretty much done with this derivation over here. There you go. Does it look familiar to you guys? When you say this, you don't have to do anything anymore in your life. You can tell right away, Ajahn, it's a simple harmonic motion. Why? You want to figure out the theta that get differentiated twice, get back the original with a negative sign. What else could it be? Theta must be sine or cosine. The factor that shows up in the front will give you the square root of, the square root of this factor will give you the omega right there. And see, you see the common pattern over here now. Whenever from now on, you see the equation that look like this, d2 by dt2 equal to negative omega square. Solution is simple harmonic. You don't have to do anything anymore. I can tell you right away. All right. Theta is equal to, all right, solution theta as a function of time is a sine or cosine, your pick, omega t plus some delta. I'm done. Wow, right, I think this deserves an extra emoji over here, guys. But what I'm saying over here is the theta is fluctuating in a simple harmonic way. It just go back and forth, described by sine or cosine function. All right, thank you for the emojis, guys. That's very good. That's it. See, this is how cool it is. And this is it. Do you notice omega is root G over L? What does it mean? This is your natural frequency, guys. So that means for one particular setup, you have a particular length of the string. Mass is irrelevant. You don't even have to care. You can put like a whatever mass on it, it's still oscillating at this omega, root G over L. So the factor that actually come into play is the gravitational gravity, the gravitational acceleration. That is the one that actually needed in this calculation. Cool? All right. So the only way that you can change the frequency is you have to change the length of the string. You have to make it longer, you have to make it shorter, or you have to change the G, which is harder to change, but you can, if you want to, you can ride SpaceX to Mars and do the experiment there. That will be fine. Or go to some super high mountain or whatever, change the G a little bit, then your oscillation frequency will change. And this is how they make clock back in the day, right? The pendulum clock. Because once you adjust the length of the string and you let it swing, it's going to swing at particular frequency all the time. So you can use this as a timekeeper. You can keep time, if you set the swing to be exactly at 1 second, so every cycle of the swing will be equal to 1 second all the time. All right. The only thing left is just you have to keep it swinging. All right. Just but as long as it's swinging, it's gonna have exact same natural frequency at all times. All right. I think this is gonna be cool. All right. Just to show you how cool this thing is, I can extend this concept of seeing this type of equation means it's a simple harmonic motion. I can expand this one to another example. All right. And just want to confirm that you guys understand what I'm doing over here. All right. So, okay, this table right here on passing, just in case you guys curious, this is it. This showcases how close it is between sine of an angle and the angle itself. So that's why, as you can see, up to about 10 degrees, see, pretty close. Sine theta and the theta are almost the same. And if you run like 1 or 2 degrees, see, up to 4th digit, they are exactly the same. So when the angle is really small, sine theta can be approximated as theta. That's a valid approximation there. All right. So usually in the textbook, they prefer to have the angle to be not beyond like 10 or 15 degrees, because otherwise then the error is going to get too great and your experiment will be off. Anyway, but pendulum is still oscillatory behavior, but except that when the angle is large, it's not going to be simple harmonic anymore. So it's not a simple sinusoidal function. Okay, but when the angle is small enough, well, it's approximated to be. So I hope this is a secret that get revealed today. The pendulum is not perfectly simple harmonic. It's approximated. Okay, all right, but anyway, for us, that's good enough. Guys, this is the ultimate example of the day. All right, we're going to extend this to something more realistic, more physical. So that's why they're going to use this concept on an object that has sizing. So as you know, it's an extended object. Like you hanging like something on the wall and let them, move, oscillate back and forth, or maybe your hand, your arms, when you're walking, when you walk, your arm is actually going back and forth, your leg going back and forth, on and on. So this is realistic stuff. So that's why this is more physical. Guys, give me equation of motion of this one. All right. Bojan, this is now is an extended mass. So sigma F equal to MA might not work anymore because you are looking at the rotation. So now there is a rotation. Every time you think of rotation, what do you think of? You think of the second law, but in a rotational form. Sigma torque equal to I alpha. Remember this one? Okay, so it's an equivalence equation, right? In a rotational rotation. It's a rotational movement. So remember how to calculate torque, guys? Okay, torque, a review. Don't worry, we're not going to do mechanics anymore, but this is just a quick review. If you guys don't like this one, don't worry about it. We're not going to do this many times. So it's an R cross F. So the force multiplied by the directions, the distance from the direction of force and the axis of rotation. All right. This I over here is the moment of inertia. Still remember that one? Some of you like, OMG, Dan, I don't want to deal with this anymore. All right, and the alpha, this is the angular acceleration. Wow. All right, so that means everything turned rotational. Everything just go in circle or in curve or whatever. So it's not going to be sigma F equal to M times A anymore, but it's going to be sigma torque times the moment of inertia and the angular velocity, acceleration, sorry, angular acceleration. All right, so just don't want to deal with this equation too deeply. What is torque? Well, Dan, torque is not bad. Torque is just, think about it. You have mass hanging at the pivot point, and I just wrote it at point O. So that's your pivot point right there. The only force that acting on this one that generate torque is the mass of the object itself. So you can say that that's the mg right there that's doing all the torque. So how much is the torque by this mg? So it's going to be the force times the distance between the direction of force. So let me draw the direction of force for you here. Here we go. This is the direction and the distance between this to the pivot point. So this is it. This is your R right here. Let me put perp sign just to say whenever you want to make a measurement of the distance from the line of force to the pivot point, you do it in a perpendicular fashion. That's all. Okay, so that's why if the distance from the CM, which is going to be your position that you assume that the mass is concentrating on that point, the center of mass, the pivot point to the center of mass is D. If the angle right now is theta, so your R, the distance, is going to be D sine theta. Cool. So that's it, guys. So torque is going to be D sine theta times mg. Nice. All right. For those of you that don't like this one, that's okay. We don't need this. All right. But I think it's kind of good for those of you that recognize this force and torque and all the stuff. It seems to, It might help you get connected with stuff that you have learned back in the 101. But don't forget, torque is a vector anyway. So think about this, Bachan. Look at the CM. The CM here trying to rotate this mass in the clockwise direction. You guys with me? So if you do the right hand rule and you curl your finger in the direction of this rotation, your thumb will point into the screen. So that means the torque over here is pointing perpendicular to the screen inward. So it depends on your direction now. In general, I mean, if anything that go counterclockwise, that will point to your face. That's perpendicular to your face. That is your positive direction. You rotate your forefinger, your thumb point toward your face. That is your positive. Then that means the torque by the mg is doing the clockwise rotation, this one, and it's going to go into the page. That is going to be your negative direction. And that's why I want to put the negative sign here. And that's it. That's why your left-hand side, it looks like negative mgd sine theta. Isn't that nice? All right. And then the moment of inertia is there. The moment of inertia is usually given for a particular type of object. It depends on the shape of the object. So let's say you are known, you get the information about the I, the moment of inertia of the object. So that's good. And now you times the acceleration, but once again, the theta is just like x. The velocity you got from dx by dt. So you're going to get the theta by dt to be angular velocity as well. So this one is omega equal to the velocity there. If you do the second derivative of x, you get acceleration A. Same thing will happen to the theta, but then you're going to get the angular acceleration. You guys with me? So that means this term right here is just your alpha. It's a second derivative of theta with respect to time. All right, guys. Moment of truth is right here. It looks almost what we want. I'm just going to rearrange this one more time for you and move things to the other side. I mean, keep it on one side right there. There you go. And you say, oh, Ajahn, almost, but not there yet. I can see theta on the left. I can see theta on the right, but it's a sine theta. Don't be afraid, guys. Let's do it one more time. Approximate it to be theta when the angle is small. So that's it, guys. There you go. Bam, bam. That's it. So when the angle is small, d2 theta by dt squared, dt2, sorry, equal to negative mgd over I theta. Do you have to solve anything anymore? The answer is no. Ajahn, that's it. Theta on the left, theta on the right with the negative sign, simple harmonic motion with whatever the factor that goes in the front, take the square root, that will be your omega right there. And the form of the equation look exactly the same as before. This is the simple harmonic motion equation, guys. So anything that can put in this form, you don't have to think of anything anymore. You can say right away, Ajahn, my theta at any time t is going to look like sine, a, sine or cosine, you pick, omega t plus some extra constant, and we're done. Any emojis for me, I think? Or what's this? ORZ? I don't know. Too many. I don't know. It's like abbreviated of something, shortened for something. Oh, from the emoji. Doesn't look good. It doesn't look good. All right, guys. So that's it. I think. I don't know. How do you like this lecture? I think this is very cool, and it's kind of like give you a very close connection from the Newton's law, no matter it's the translation Newton's law or it's gonna be like a rotational Newton's law, but that gives you the simple harmonic motion, no matter what. So the only thing that you want to take home today is this, dude, right here, guys. This is it. This is the equation that you want to take home with. From now on, in your life, anytime that you have second order differential equation, the reason it's second order because it's second derivative right there. Whenever you have second order derivative, differential equation that looks like this, you don't have to solve anymore. The answer is definitely sine and cosine. Be done. Okay, so the last stop that I want to do today, because right, it's online. I know you guys probably not gonna feel much of learning anything through the screen here. I'm just gonna look at the perspective of the energy, and I think we are done. Sounds cool? So if I ask you about that, because you already use like mechanics, Newtonian mechanics and all this stuff, so and you already talked about the displacement, talk about the velocity, acceleration, Newton's law, on and on. What about energy? I would say about that. Can you calculate energy for me? I say no problem. Why? Because go back to the case of mass on spring as an example. Once I solve this sigma F equal to ma stuff, I got my solution. I know everything, guys. So just to make it simple, let me calculate the energy of the mass on spring for you and see what you get. All right. I know everything about this mass. I know how it moves. I know the velocity and everything. So what is the energy of the system? Of course, Ajahn, the energy has only two terms. It's either kinetic energy or potential energy. And because it's mass on spring, only two energy involved over here is going to be kinetic energy, 1/2 mv squared all the time, which is fine. And mass, I mean, it's a spring potential energy, so it's going to be 1/2 kx squared all the time. And now you start to laugh, or John, easy. X is known, V is known, X is known. No problem. I just plug in everything. All right. So you guys follow me. It's going to be super duper at the end. Plug in the X. You guys do remember X is A cosine omega t plus some constant, right? You just square it. So it's going to be A squared cosine squared. Velocity, no problem. You can flash back if you want. The velocity is just negative A omega sine omega t. Or, I mean, if you want to do it quickly, you can just differentiate it once. That is fine as well. So what you have is you just say omega A sine omega t plus constant. The negative side disappears because you square it. So negative side just go away. And you just add these two together. So the net energy is just kinetic plus potential. Plug it in there. Now, well, Ajahn, we know that omega is square root k over m. So that means I can plug in that k over m on here. With me, guys? Okay, you guys with me? So once I plug it in, what I have in the front is going to look like 1/2 m k over m. So m cancel. So actually it turns out that m omega square is just k. Cool. So I have a common factor of 1/2 ka squared. I can pull it out from those two terms. What I have left, sine square plus cosine square, and everyone still remember this identity over here. Sine square plus cosine square is equal to 1. And that's it, guys. Isn't that amazing? No, Dan, of course it has to be because it's a conservation of energy. Imagine that you have a spring. You stretch the spring out. See, starting from here. You stretch out the spring all the way to the maximum displacement, right? Right there. Okay, wait for the screen to refresh a little bit here. All right, so here we go. So you're sitting right there. Okay, so that's, let's say this is your starting point because you're starting from the maximum, your cosine function is here. But I mean, you can start any way you like, doesn't matter. But for now, let's say this is your starting point. So what is your total energy at this point? It's 100% 100% potential, right? At this moment, it's 1/2 ka squared. There's no movement. Velocity is 0, so it's 100% kinetic energy. That's why this is going to be your total energy in the system. But this expression that we just got right here from adding the kinetic and potential energy at any time is a guarantee. It is saying that at any moment in time, the sum of the energy of the system must stay the same. Then check. Done. Isn't that cool? All right, because I'm not having any terms, or I mean, sorry, I don't have any things that gonna take away my energy. Everything is sort of like oscillating on a smooth surface and everything, bow, 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 so energy stays the same. So that's it. In conclusion, conservation of energy give you that at any time, it's just the interchange between kinetic energy and the potential. Whenever you have the maximum potential, the kinetic will go smaller. Anytime you have a higher potential, or I mean, what, higher kinetic energy, the potential will go lower. But at any time, the sum must be exactly the same, 1/2 Ka squared. Cool. All right, guys, and I think that's it. We are done. Sounds like a good plan here. All right, and I think we can discuss more what happened when you have a friction in your system and something take away the energy. The conservation of energy doesn't hold anymore. What will happen to the oscillation? And that we can discuss on Wednesday. All right. So I try to keep the content a little bit to the minimum over here, because not only we do it online, but I think you guys still have like first exam to go through. So don't want to push too hard here. All right, guys. So I think that is it. Any questions? Already. All right. So if not, then all right, give me the final emoji and then we say goodbye. Sounds good.
Ajahn, I
Oh,
have
question.
some
Yes, go ahead. Yes.
About the test one, is
Yeah.
only the topic in the week 1 to week 3, right? So like
Correct. Just thermodynamics. Correct.
okay.
So it's going to be handout 1, 2, and 3. Yes.
Okay. Thank you.
Okay. Right. Thank you very much. All right, guys. Go to sleep. All right, guys. So see you on Wednesday.
Ajahn, it's on the 21st, right?
Yeah, 21st. Yes. I'll put an official announcement soon. Yes, but it's
all right. Thank you.
Yes.
Ajahn, where are you going to post the recording?
I think I'm gonna do YouTube, so I'm gonna upload the YouTube there. So I'll post the video along with the old video as well. So I'll process them and I put them on. I can do it.
Okay,
I think yeah, by the end of tonight. So everything should be up. Yes.
Thank you.
Thank you. Yes, 21st. Oh, actually, I will have 2 sessions. So it means you can start at 4 p.m. to 6 p.m. like we discussed in class. But for the first session, you have to stay until 6, right? Until the second session starts, and then you can leave. And the second session start at 6 to 8. Yes.